Hi, thank you for having me today. I'm TY. I lead the adaptive streaming algorithm effort at Netflix. When I was preparing for this talk, I was thinking through how do I explain the connection between congestion control and live and low latency. But I think after the panel, probably you already have the context of the importance of the congestion control algorithm plays in live and low latency. So at Netflix, adaptive streaming algorithm wasn't designed in isolation. And in fact, we have to work with congestion control algorithm designs to make sure things works optimally. And if there's one thing you can take away from this talk, I hope that is the following. That is, adaptive streaming algorithm and congestion control needs to work together. And if they do so, that can create less bursty traffic as well as better QoE. Netflix has rolled it out for our video on demand traffic, and we are looking to live traffic next. And YouTube is actually doing similar things. They are experimenting with similar ideas. And in fact, we are working together with them to quantify the benefit of having the ABR and congestion control working together in a residential network. And we have a paper submission in progress. And so hopefully you get away from this talk that combining adaptive streaming algorithm design and congestion control is good for everyone, and you should try it out. All right, but to understand where the benefit coming from, we need to think through how does ABR work today. Today, it's kind of like work independently from the congestion control. So adaptive streaming algorithm initially take a video rate and use that rate to download a video segment or two. And then we measure the available bandwidth based on TCP or whatever congestion control algorithm you operate on top. And then take that into the consideration together with other variables like player state and other things that ABR algorithm need to think through, and use that to make a decision on what's the video rate we should pick for the video segment, and download that and rinse and repeat. And of course, you need to think through, is there a space in the playback buffer? If not, I have to pause. If there's a space, then I can proceed, and etc. And so from this picture, you can see that adaptive streaming algorithm logic is built on top of the congestion control algorithm, but they are not necessarily informed with each other. But the decision of it is kind of intertwined with each other. So it's kind of mingled together. And this kind of mingled situation leads to several problems. One of them is downward spiral. The congestion control algorithm can mislead the adaptive streaming algorithm to choose a lower video rate. And the lower video rate can interfere with congestion control algorithm and lead it to grab less available bandwidth and so on and so forth. So this is kind of one of the effects, but there are other impact as well. And in 2023, in SIGCON, we published a paper showing the benefit of having these two logic kind of work hand in hand together, and there are many benefits coming out of that. So where is the benefit? In order to understand where the benefit comes from, we need to understand what goes wrong in this picture so that we can know where can we do better in this picture. All right, so the fundamental issue here is that congestion control is designed to fully utilize the bandwidth and fully utilize its own fair share. And so from the design principles perspective, it is trying to download as fast as possible. The question is, do we need that for video traffic? Video today is usually not throughput limited. So if we look at 10 years ago, 2010, the throughput average is about 5 megabit per second. Fast forward to today, it's about 200 megabit per second. And if we look at the need from the video traffic, it's the growth rate of the top video rate is actually much slower. thanks to the advancement in our encoding technology. So kudos to all the encoding folks in the crowd. And so if we look at today's top video bit rate, it's roughly around 20 megabit per second. And so the throughput, the average throughput is about 200 megabit per second. So that's at least 10 times more. For typical Netflix sessions, we are looking at average throughput is about 13 times more than the top video bitrate. So what does that mean? That means, do we really need to download as fast as possible? Maybe not. But the problem today is that congestion control algorithm is downloading the video segment as fast as possible. And so these combined with the fact that we usually have limited playback buffer and our throughput is often a lot higher than what we actually need, what does that mean? That means the traffic is pretty bursty. So if we play it out in real time, what does that mean? At the beginning of the video playback, because the buffer is pretty empty, so we will try to download one video after another, and congestion control algorithm will try to fully utilize the throughput. And then our buffer is full, and so now what? We have to pause and wait until the buffer drained to the point that we have enough space to download the next segment. And so, and then congestion control algorithm kicks in, we fully utilize the bandwidth, fill the buffer entirely again, wait, and then so that means pause, and then rinse and repeat. So you got these on-off traffic pattern. So that's pretty bursty. What's the ideal situation? Ideally, because we don't need that much capacity, right? Ideally, if we can smooth that out over time, we will get a much smoother traffic pattern. So what does that mean? That means less queuing delay. That also means less packet loss. And that means smooth available bandwidth for everyone sharing the same link. And the impact of bursty traffic is actually very visible, especially for delay-sensitive traffic. So in the following, I'm going to show you a demo video where a Netflix gaming session, which is delay-sensitive, and this gaming session is sharing the bottleneck link together with a video-on-demand traffic. All right, so in this video, you can see the upper right corner is a the cloud gaming session sharing the link with unpaced video-on-demand traffic, and then the lower left is the gaming session shared with a paced video streaming session. So you can already see some stuttering that just happened on the upper right, and versus on the other hand, when the gaming session shared with the paced traffic, it's a lot more smooth. And you can substitute the gaming session with low latency, which is also delay sensitive as well. All right, so if we don't need congestion control to download video segment as fast as possible, what do we need congestion control to do? We just need it to download as fast as adaptive streaming algorithm needed, so that we can maintain the same QoE. And this is what we call application-informed pacing. All right, so in our SICOM paper, we laid out a very simple algorithm. That is, we inform the congestion control algorithm to pace a rate at a multiple of the top encoding bit rate. And this pacing rate can be a linear function of the buffer state, but this is just one of the algorithm design. It doesn't need to be it doesn't need to be exactly this form. As long as it's more than adaptive streaming algorithm needs to maintain the QoE, it can work. And if we put this into perspective, even though we are designing the pacing algorithm to be fairly generous, to be multiples of top bit rate, if you put that into the perspective of what's available out there, it is a very small margin of it. And if we look at the results, it's pretty interesting, both in terms of the networking characteristics as well as QE. So here I'm only focusing on the networking metrics. We reduce the instantaneous throughput, which means that we reduce the burstiness. And we also reduce the retransmission, which is a proxy of the packet loss rate. And also the round trip time, which is a proxy of the queuing delay. And this is the network part of it. We also see improvement from the QE's perspective, because interestingly, when you operate these on the low-end devices, the smoother packet arrival pattern also help with the CPU consumption on the low-end devices, and that can help lowering the media interruption rate on devices as well. So these are pretty promising results towards combining adaptive streaming algorithm design and congestion control algorithm design together. So what now? As I mentioned, we have rolled it out for video on demand traffic, and we are looking into expanding that to live. As I mentioned in the beginning of the talk, YouTube is experimenting this. Per my understanding, is on both live and SVOD, and they are seeing benefit just like we do. We are working with a university on their residential network to quantify the results, and as I mentioned, the paper submission is in progress. And if you want to try it out, but you don't own a CDN like us or YouTube, well, CMCD can kind of help you communicate the intent to the CDNs, and you should talk to Will. And if you want to know more, please come find me and let's chat. And I think I have a couple minutes for questions.
Any questions? Yes, Pierce. Can you just shout?
Do you alter the slow start?
Do we also do pacing at a slow start? Yeah, so we do have a few parameters to fine-tune the slow start behavior. Although slow start usually happen in the beginning of the sessions, and in the beginning of the session, you do want to accumulate buffer level faster. But as I kind of hinted from how we design the algorithm, the way we design the pacing rate is kind of as a linear function towards the buffer level. So we take the buffer level into account, and that kind of help us to facilitate or balancing the need between ABR and the need of accumulating buffer and also the slow start behavior. Oh, are you talking about like receiving window? Right. Yeah, so if you're application limited, you are kind of pacing the congestion.
Hi. Yeah. So when you send a segment and it may be 2 seconds, but then there's a gap. Mm-hmm. And so in that gap, you might send at full rate of the segment, and then there's a gap. And so during that gap, then the theory is, according to the sort of RTT, then you decay the congestion window in between each segment. So I wasn't sure whether you played with that at all, because in some senses maybe you're in a normal TCP, maybe you're going to be higher than you need to be, and the congestion window will decay, and then it'll maybe hit a better spot.
Yeah. Right.
Just-
So yeah. So you will starting from a different point if you decay.
Yeah.
But the problem with TCP or congestion control is you still ramp it up pretty quickly, and you still end up trying to fully utilize the full capacity. And the segment is usually a few megabyte, right? So you would definitely reach up to the at least the TCP will try to reach up to the full utilization. So the problem is still there.
Yeah, true. Are you using a sort of BBR-based TCP, or is it loss-based?
No, we're using a new Reno-based congestion control algorithm, but it's Netflix optimized.
Okay.
But YouTube is using BBR, and
Yeah.
they are seeing similar results.
I mean, I think quite a lot of CDNs are using a BBR. Just wondering, because that doesn't seem to be as good. I don't know what all of them do, but the congestion window decay doesn't always seem to happen quite so well. But
Yeah.
anyway, thanks.
Thank you. Very quick question, please.
A quick question. So, since the pacing strategy is a critical part to get the gain, but under a network, if there are multiple downloading things, they are competing the resources. Does that mean we need to apply the same pacing strategy to everybody? Because if someone still uses the aggressive strategy, the other will be hurt.
Right. Yeah, I think this applies to all the network algorithms sharing the resources. How do we take the fairness into consideration? And if we think about how congestion control works, right? When people design congestion control algorithm, we also need to discuss what's fair means. And I think that's also applied here. And that's why we as a community need to talk about these kind of things together.
Thank you.
All right. Thanks to speak.